So let's consider an RC filter. So if we had a resistor and then we had a capacitor, so what would happen if we fed it with a voltage source which was initially 0. So basically it had 0 volts initially, like a step, and then we turned it on, so now let's say it's 1 volt. So we know that a capacitor, when it is in steady state, so basically if it is a DC, the capacitor is an open. So let's see if we can predict something from that. So before this change, let's say this is at time t equal to 0. So this change happened at time t is equal to 0. It's just a reference. I'm saying that's when the interesting things happened. It could have been at any time. It's just time t equal to 0 is just a reference saying this is when something changed. So a long time before that, here the voltage was always 0. So if the voltage was always 0, then I can consider my capacitor as an open, which means I don't have to take a look at it. And since this is an open, the current going through this resistor is 0. So this current I was actually equal to 0. So if this current is equal to 0, that means the voltage across the resistor because of Ohm's law is also 0, which means this voltage is at the same, this node is at the same potential as this node, and since this is at 0, this voltage is also at 0. So we figured out, okay, fine. So because of the fact that we know that capacitor is an open, we know that this voltage is going to be 0. Now let's see, this thing has changed, something has happened. So finally, after everything is said and done, this is a DC voltage of value 1. At that point again the capacitor is 0. A capacitor is an open. If the capacitor is an open, the current is 0. And if the current is 0, that means this voltage is at the same potential as this voltage. So we initially start with 0, we'll finally end up with 0, and there's something that's going to happen in the transition, which is what we need to figure out what it is. So one way of solving this equation is to actually go ahead and solve the current and the voltages. So we'll do that now. So if you assume that there is a certain current flowing through this whole circuit, so there's a current I, then the same current I is flowing through here also, that's also I, and the voltage at this node, let's say, is V1, because this is node 1, this voltage we'll just call V because that's the input. So what we know is that the current I is C into dV by dt. Okay, and this is because of course Q is equal to C into V. So derivative of Q is I, so capacitance is a constant, so I get dV by dt. Okay, so now I just have to write that this voltage, which eventually is actually 1, so it's I can assume that everything is starting from after 0, because before that the voltage is 0. So I'm going to say at all time it's going to be 1 from here onwards. Here onwards is always at 1. So 1 is going to be equal to the voltage across this resistor, which is IR, that's the I, plus the voltage here, which is V1. So that's it. And V1 is also changing and I is also changing. So basically I have 1, which is equal to I into R plus V1. Sorry. Okay, this is not I, this is 1. This is the voltage. So this dimension is voltage, this dimension is voltage, this dimension is voltage. We must be doing okay, something okay. So I we know is this. So I get C into R. Usually we write this as RC. So we have RC into dV1 by dt plus V1. And we know that this is supposed to be 1 after time t equal to 0. So V1 is 0 before that, so that's not relevant. So if you are familiar with ordinary differential equations, then you know the solution for this. But if you think about it, if there is one more capacitor in the circuit, I'm going to have another second order, another derivative, and then to analyze a circuit with so many derivatives is really hard. So we don't actually solve differential equations to well, you can, but beyond the first and second order probably we don't usually use the differential equation to do it. We use a completely different technique which makes it into a simple algebraic expression, and that's how we solve it. So anyway, in this case, well, I'll just tell you V1 is equal to 1 minus e to the power of minus t by RC. And if you substitute this, then it sort of all works out, because there's a differentiation. The differentiation of a constant is 0. The differentiation of an exponent is this part would just come down. So 1 should be equal to, and this is whole thing into ut. It only exists after time t equal to 0. Before that it's 0. So 1 becomes equal to RC divided by this RC, and there's also a minus, so the minus cancels, so e power minus t by RC plus 1 minus e power minus t by RC. There. Okay, so since this becomes 1, this and this cancels out, and so you're only left with 1. Okay, so it satisfies this expression. This is not the answer, we are just checking if the answer is correct. So this is what the voltage looks like, which basically is an exponential characteristic here, which means only at time t equal to infinity will this actually become 1. So technically it never charges, but that's not interesting. It's charged enough after even 1 RC time constant. This is called a time constant because it has the same dimensions of time. E power, this has no dimensions, this is time, this is also time. So if you multiplied R and C, you would get something that we call a time constant, and as soon as it is 3 time constants or 4 time constants, you say it's settled enough. So why am I doing this? Yes, now we know what capacitance is, and so now we know how it will charge. But if we had to do this and we had a circuit in which we had many resistors, and many capacitors, well, which are all ground, and we feed a unit step, basically fat chance to be able to solve something like this with this current, this current, this current. You're going to have lots of differential equations, very hard to solve. So the moral of the story is we don't do solution of ordinary differential equations. We do solutions of ordinary differential equations, but in an entirely different way, using Laplace transforms.